I chose to make a website about hemophilia. Hemophilia is very important because it affects nearly 400,000 people worldwide. Of that, about 20,000 of them are within the United States. This disease is caused by an X-linked recessive mutation that alters the concentration of important coagulation factors in the blood, and males are much more likely to be affected because it is an X-linked recessive mutation, meaning that in males, they have one X chromosome and one Y chromosome. All they need is one mutant X chromosome in order to get the mutant phenotype. The effects of this disease are life-altering, and they can be fatal. And simple genetic pedigrees like the one in the practice problem set can help expecting parents determine the probability of having an affected child. And a copy of these practice questions can be found on the website under the Practice Problems tab. So the first question asks us to define an autosomal recessive trait. An autosomal recessive trait is a trait that has its genes present on a somatic or autosomal chromosome and requires 2 copies of the recessive allele to have its resultant phenotype be present. The definition of an X-linked recessive trait is a trait that has its genes present on a sex chromosome, in this case the X chromosome because it says X-linked. In females, 2 copies of the recessive allele are needed to produce the mutant phenotype, while males only 1 copy is needed because males have 1 X chromosome and 1 Y chromosome. So this next question asks what the mode of inheritance for the above pedigree is. So squares represent males, circles represent females, and if the box is shaded in, it means the individual is affected. So here we can see that there's not a typical 3-to-1 ratio, so we can kind of rule out autosomal traits. So we assume it's sex-linked then. And then because the phenotype can be hidden in a generation, we know that it's sex-linked recessive because the females do not display the mutant phenotype and only the males do. And so the males display it at a much higher rate because they only have 1 copy, so then we can assume this is X-linked recessive. So this next question asks us to list the genotypes of each individual in the diagram pedigree. So first, I like to start off by doing the affected males because we know their genotype it has to be X-ay because they have to have 1 mutant copy of the allele on the X chromosome. And then I like to go to the unaffected males because you know their genotype is X-ay. Then I like to go to the carrier females because we know that they have the X-A and then X-a. And then I like to go to the females who we don't know what their genotype is. So first, let's start with the affected males. So individual 1-1, we know they're affected, so they have to be X-ay. And then for the same reasoning, because the box is shaded, individual 3-3 is X-ay. Individual 3-6 is the same. Individual 3-7, 3-8, and 3-11. Next, I like to go to the unaffected males. So I'll start with the second row. So individual 2-2, their box is not shaded, so we know they're unaffected. So their genotype has to be X-ay. For the same reasoning, individual 2-4, the same genotype, individual 2-6, 2-8, and 2-10. Also, the same reasoning can be applied for individual 3-1, 3-2, and that's it. So those are all the males done. That's the easy part. Next, we have the females to do. So let's start off with the females that we know are carriers of the disease. So the second row, all the females have to be carriers because they're not affected, so they have at least 1 good copy, but their father can only pass on 1 recessive copy. So we know that all their genotypes have to be X-A, X-a. So this is true for individual 2-1, 2-3, 2-5, 2-7, and 2-9. So we have those ones figured out. And then the last individuals are the ones that are not listed. We don't know their complete genotype. We know that they do not contain 2 copies for the recessive allele, but we do not know if they're carriers or not. So we give them the denotation of X-A and then X-line, so they can be either a big A or a little a. And so this is true for individual 1-2, individual 3-4, 3-5, 3-9, 3-10, 3-12, and 3-13. The next question asks, what is the probability that the child of individual 3-3 and 3-9 is heterozygous if the mother is heterozygous? So first here, it's a question within a question. Because it says that the child is heterozygous, we know that they have to be a female because they have 2 copies of the X chromosomes. So they'll need to get 1 good copy from mom and 1 bad copy from dad. Because we know that individual 3-3 is affected, we know their genotype is X-ay, and then The question said that the mother, also known as individual 3-9, is heterozygous. We know that their genotype is X big A, X little a. So there's a 50% chance that the father gives an X chromosome that is defective, and there's also a 50% chance that the mother gives a X chromosome that is not defective, or with no mutation. So the probability is 0.5 times 0.5, which equals 0.25. So the next question asks, what is the probability that individual 313 is a carrier for the disease? So we know the father is an unaffected male, so his genotype is X big A Y. We know the mother is a carrier, and her genotype is X big A, X little a. Since we know the offspring is a female, we know that the father must have given one copy of the X chromosome, and he only has the X big A allele. So the mother has to give the X little a allele, and there's a 50% chance of that because she has X big A, X little a. So the probability that individual 313 is a carrier is 0.5. The next question asks, if individual 3-4 and 3-6 have 9 children together, what is the probability that they have 4 girls and 5 boys? So this requires the use of the binomial expansion theory. So here it is. It's a little complicated, but it's really easy once we get to use it. So we know that the mother's genotype is XX and the father's is XY. So the mother can only give an X chromosome, but the father can give an X or a Y. So the father has a 50% chance of giving an X chromosome, and the mother has a 100% chance of giving an X chromosome. So there's a 50% chance of getting a female, and there's a 50% chance of getting a male. So we know that we can plug this into the formula now, and we know that there's 9 individuals total. And so we have 4 girls and 5 boys. And then we do the 50% chance to the 4th power times 50% chance to the 5th power. And this equals 0.246. The next question asks, for the parents described above, what is the probability that they have 5 boys and 3 of them are affected? So this requires the use of the binomial expansion theory again. And so we also know that there's a 50% chance of getting a male or a female. And so we did the exact same calculation before, so we get the 0.246, but there's a little bit extra we need to do to it. So the mother must be a carrier in this scenario because 3 of her children, which are boys, are affected. And this can only happen if she passes down a mutant copy of the X chromosome and the father passes down a Y chromosome. We also know that the father is affected, and his genotype is X little a Y. However, the father's genotype doesn't affect the probability of a male being affected because the father can only give a Y chromosome to males. So we need to figure out the probability that the males are affected. So we can cut out the female section, and we know that the father is going to give a Y chromosome and the mother is going to give an X chromosome. So the mother would have to give a recessive X chromosome. So to determine this, we have another binomial expansion. So we're going to multiply these two together because the keyword "and" in the question. So we have 5 factorial over 3 factorial times 2 factorial, and then times 0.5 to the third times 0.5 to the squared. So we use 3 because 3 of them are affected, and then 2 because it's 5 minus 3 is 2. So the probability that the boys are affected is 0.5 because if the mother is a carrier, she can either give a recessive copy or a dominant copy of the allele. This results in 0.3125. Lastly, we need to multiply these numbers together, and we have to account for the fact that the mother is heterozygous and she's a carrier, so we have to multiply that by 0.5 because she can either be homozygous dominant for the dominant allele or she can be heterozygous.